All right, let's continue on now with bond rotation. And for our alkanes, just our normal alkanes, all the carbon-carbon bonds are sigma bonds. They're just single bonds, just a sigma bonds, and sigma bonds can rotate. So if you have, say, this molecule right here that I made, you can rotate any of these. See, this bond here will rotate just fine. You can rotate like this. This one will rotate like this. This one over here will rotate. Molecular models, I highly recommend getting some molecular models. Sit around, eat some bacon in the middle of the mall, playing with your molecular models. Everyone will think, man, you're a smart person. And you will feel smart, and then you'll do better on the next exam. So yeah, play with your molecular models, and you can see how they have rotations. Yeah, I can see this bond can rotate. So I can rotate these two groups to be right next to each other like that, or I can rotate it like this. I can do all sorts of different rotations of these molecules because single bonds can rotate. And note, if you have a long chain of carbons, note, you can put it in like the line structure format. When we do line structures, we tend to make them look like this. Up, down, up, down. All right. But note that since they rotate, it doesn't have to stay like this. This can come over like this. Note that this carbon at this end, right here, and the carbon at the other end, these two carbons right here, with just two bonds rotating, this one here and then the next one, those two carbons can get awful close to each other. So when in solution, these bonds are rotating all the time. Single bonds are rotating all the time. So your molecule, your alkane, is never just going through the solution like this. It's not doing that. It's not going, hey, I think I'll just run this way. It's always doing this type of thing. It's just rotating all over the place in solution, just going crazy because all the single bonds are rotating as it moves. All right. Well, this leads us to various conformations or conformers. These two molecules are the same because all I did was rotate this bond here to bring these two down. These two are the exact same molecule. They're just in a different conformation. Well, we need ways of drawing those conformations. The first way is what we're going to call the sawhorse formula. When we say, let's start with something easy, let's look at this little molecule right here. And if you're doing the sawhorse formula, you're going to say, okay, the two lines between the two carbons, I'm going to make go like this. Here are these two lines like this. Here they are here. And then this carbon here represents the back carbon. It's kind of coming out towards you. This carbon up here is the front carbon. Or excuse me, this is the back carbon going away from you. This is the front carbon coming out towards you. And in this sawhorse drawing, can you see that I've got this one going down, which is this hydrogen, this one coming out at us, and this one back here going back. And here, this one's coming out towards us this way, this one's going kind of back, and this one's going up. So this one coming out here is this one, the one my fingers are on, or this one going back, and this one going straight up is this one. You need to be able to look at this and see this in 3 dimensions. All right. Another way is a Newman projection. People said, oh, the sawhorse is tough to see, so I'm going to line up these two carbons in line with the camera, and so I'm going to make it look like this. This is the Newman projection. So can you see the front carbon has them the 3 hydrogens here, here, and here. The back carbon has these back ones here, here, and over here. And the way we indicate that with a Newman projection, the front carbon, you actually draw the bonds going straight to the very center of your Newman projection down here. So we've got this hydrogen coming up here, which is this one, down here and here are these two. The back ones, you don't draw the lines going all the way to the center of the circle. So for Newman projection, you draw your circle. The front carbon, you have those bonds going all the way to the center of the circle. The back carbon, those bonds do not go all the way to the center of the circle. They just go to the surface or the edge of the circle. And that's how you do a Newman projection. Kind of different one, a weird one, is the Fischer projection. And first I'm going to show you what the Fischer projection means, and then I'm going to actually draw it. Fischer, so let's review. Sawhorse, you're looking at the molecule kind of like this. This is a sawhorse projection, where you can kind of see these two carbons. Newman projection, you're looking straight down the carbon-carbon bond. With a Fischer projection, what Fischer decided to do was to make the carbon-carbon bond vertical on the page. But very importantly, it's vertical on the page, but oriented this way so that any things coming off of it that are kind of going horizontal are coming out towards you. So you've got the hydrogen in the back here going back away from you, and the hydrogen also on this other side is going, right here, is going back away from you. So the vertical lines represent either something completely vertical or something going away. The horizontal lines, left and right, mean something coming out at you. If we're going to draw this, recall from Gen Chem when we're drawing Lewis structures, if something's coming out towards us, we draw these wedges. If it's going away from us, we draw these little dash lines. So these two hydrogens are coming towards us, so we have wedges and stuff like that. When you're actually drawing the Fischer projection, though, you draw this. You just draw this vertical line right here. And two horizontal lines. Wherever lines cross are carbons. Horizontal lines means these two hydrogens are coming out towards us. Vertical line means this hydrogen is going backwards. So when you see this Fischer projection right here, basically you have to say, that is looking at the molecule like this. Okay. Well, when we look at it like that, we can see, especially with our Newman projections here, we see the various angles that we call dihedral angles. For example, I'm going to take two of the hydrogens off this molecule and just replace it with a little red atom. And let's see what we have. All right. Here is our sawhorse projection. So if I make it look like the sawhorse projection, note I've got one red guy up, one red atom down. So that would be like this. So here's the sawhorse projection. Newman projection is much easier. I just have to do this. Note, with Newman projection, here's my circle. The line's coming to the center here and goes up to this guy here. So here is the Newman projection. It looks like this. There's the Newman projection. Things look a little off a little bit because of the camera and the orientation and stuff like that. But that's the Newman projection. And what we can see with the Newman projection, can you see how this red ball, if we go through the carbon down to the other side, is 180 degrees. We've got a 180 degree angle between this one and this one if we consider both of these two carbons as just 1 point. When you draw something in the Newman projection, those two carbons are overlapping each other, so we consider the two carbons just 1 point, which means these two red groups are 180 degrees apart. We call that a 180 degree dihedral angle. Because it's not a real angle in the molecule, because we need You know, here, this is a tetrahedral molecule, 109.5 degrees for this angle, 109.5 degrees for this angle. But when we look at dihedral, we're going to overlap these two carbons and say we've got a 180 degree dihedral angle. And note, if I turn this, I could turn this like here. And note now it's not 180 degrees, that's a 60 degree dihedral angle. Because if 180 degrees is all the way, this is 1/3, 2/3, 3/3, 1/3 of an angle here, 2/3 of the angle here, the rest of it here. So 1/3 of 180 is 60. This is a 60 degree dihedral angle between this red guy here and this red guy up here. 60 degree dihedral angle here. All right, or if I did it like this, check this out, 0 degree dihedral angle at this point. The two reds are kind of covering each other up, 0 degree dihedral angle. When we have a 0 degree dihedral angle, we call this the eclipse conformation. You cannot see the back one because the front one is eclipsing it. When we have a 60 degree dihedral angle, we call that the staggered conformation. So this is the staggered conformation. This is the eclipse conformation. Staggered, 60 degree dihedral angle. Eclipse, 0 degree dihedral angle. And here is the sawhorse projection of eclipsed. All right. When we look at the various deals, we know that, hey, these bonds can rotate, right? Can't bonds rotate? So can't these go from, sigma bonds can go from eclipsed, here's a different eclipse conformation, to staggered, to eclipsed again, eclipsed, to staggered, to eclipsed, to staggered, back to eclipsed. Yeah, single bonds can rotate, so they can do that. But it turns out the staggered has the lowest energy. The eclipse conformation is a little bit higher in energy than the staggered. And it's due to the overlap of molecular orbitals being different. Turns out staggered allows for some electron delocalization, which is more stable. We call that hyperconjugation. Don't worry about it. If someone says, why is the staggered conformation a little bit more stable than the eclipse? The answer is hyperconjugation. Well, what does that mean? Don't worry about it at this point. Although, if you are interested, I do recommend going and looking it up and reading about it. It's just a little bit advanced at this point for you. Take physical chemistry and then come back to me on that one. All right. Well, let's do this. Since we've got energies, let's make a potential energy versus angle of rotation diagram here. Where this is our energy, our potential energy of our system, of our molecule, and here's our angle of rotation. And we can see in the staggered conformation, we're at low energy. As it rotates up to eclipse conformation, we're at higher energy. Then it rotates back down to staggered, we're at low energy, and we're back up to eclipse at high energy. This is a 12 kilojoule per mole energy barrier, and for ethane, where we got 2 carbons and 6 hydrogens, it's a 12 kilojoules per mole barrier. It's very low. We call that a torsional barrier because we're doing a rotation. So it's a very low torsional barrier. And as long as you've increased the temperature of ethane above absolute zero all the way up to negative 250 degrees Celsius, we call absolute zero is negative 273, and room temperature is 25, so this is super, super cold still, but as long as it's above, the temperature is above negative 250 degrees Celsius, there's enough energy to overcome this torsional barrier, this 12 kilojoule per mole energy barrier, and you have free rotation. Okay. So, that looks pretty good. Now that we've got that down, let's look at the next molecule. In the next video, we're going to look at butane. Instead of nice ethane that we had to begin with, we're going to look at butane.